All right, everyone, we're going to finish our 6th unit today with topic 6.9, which is integration using substitution. The rule of integration by substitution is similar to that of the chain rule for differentiation. So there's a little look at the chain rule, something we used a lot back in first semester. From the definition of an antiderivative, it follows that the antiderivative of f prime of g times g prime would equal f of g of x plus c. Okay, or you might think of it this way: f of u times du dx, the antiderivative of that would be f of u plus c. So it's kind of like a backwards chain rule. The only difference is we're going to need to do a little work beforehand before we can actually apply our integration. So let's take a look at a couple problems here. Number one, yes, you can do this by multiplying this all out. That will require you to multiply this out 4 times and then distribute it 2x. Not ideal. Okay, so let's recognize a pattern here that we're going to use a lot. When an inside function's derivative shows up outside of that function, what would the derivative of this be? It'd be 2x, and there's a 2x. When you recognize that, it's usually a pretty good sign that we are going to use substitution. And your substitution is going to be what is inside this function, okay? So we call this in calculus U substitution. I mean, theoretically, you could use any letter you want. That's not x, obviously, because we already have an x in the problem. But in the calculus world, we tend to always use the letter U. So what we do here is we say, all right, let's let U equal x squared plus 1. If we take the derivative of this equation, we get du dx equals 2x plus 0. And if we multiply both sides by dx, we get du equals 2x dx. Hey, look at that. 2x dx is right there. So I can replace 2x dx with du, and I can replace x squared plus 1 with u, and my new integral becomes the integral of u to the 4th du. A much easier antiderivative to take than the first original equation. All right, if we take the antiderivative of u to the 4th, that's just going to be u to the 5th over 5 plus c. And the last thing we have to do is resubstitute, or unsubstitute, I guess you can say, back in our original expression. And there we have it. Problem B. Again, recognize the derivative of this inside function shows up outside of that function. So that tells me this is a substitution problem, and my substitution is going to be what is inside that function. If I take the derivative of that, and usually we do a little shortcut with this. Instead of writing du dx, we just put du over here. And we know we're going to multiply the dx over here, so we just put the dx over there anyway. So du equals 3x squared dx. And look at what we have here. 3x squared dx, 3x squared dx is du. So I can rewrite this as root u du, or better as u to the 1/2 du. Taking the antiderivative of that, we get u to the 3/2 over 3/2 plus c. And finally, rewriting that and resubstituting back in, we get 2 x cubed plus 1 to the 3/2 over 3 plus c. All right, finally, taking the antiderivative of c. Recognize that, hey, we have an inside function right here whose derivative is right here. So we're going to substitute for tan x plus 3. So that would be du equals secant squared x dx. Secant squared x dx all becomes du. So now my integral becomes just u du. Antiderivative of that would be u squared over 2 plus c. And if we resubstitute, we get tangent x plus 3 squared over 2 plus c. Those are nice ones, where everything works out nicely. Sometimes our du dx is not a perfect match for what's on the outside. That's okay. As long as everything but the constant matches, we're in good shape. So what do I mean by that? Let's take a look here. X squared plus 1 is on the inside. Just x on the outside. Well, the derivative of this would be 2x. We don't see a 2x here, but like I said, if we're just missing a constant, we can adjust to that. Let's take a look at how this works. So I'm going to let u equal x squared plus 1. So then du equals 2x dx. But I don't want 2x dx, I want x dx. So I can simply solve this equation for x dx, and I get du over 2 equals x dx. So now I can replace x dx with du over 2, or with 1/2 du. So my integral now becomes 1/2 u to the 6th du. And it might be even better to write that 1/2 out in front, u to the 6th du. And now I can take the antiderivative of that, and I get u to the 7th over 7 plus c. So simplifying and rewriting, I get x squared plus 1 to the 7th over 14 plus c. Minor adjustment to get that 1/2 in there. So again, we have a derivative here of just 2, which is just a constant. We can make do with that, no problem. Let's substitute for the inside function, which is 2x plus 1. And my derivative would be 2 dx. But we just want dx. That's it. That's all that's there. So if I divide both sides by 2, I get 1/2 du equals dx. Now I can rewrite this as 1/2 the antiderivative of u to the 1/2, or root u, but I'm going to write it as u to the 1/2, du. Taking my antiderivative, I get u to the 3/2 over 3/2 plus c. And rewriting and simplifying, I get 1/3 2x plus 1 to the 3/2 plus c. Question C. Here's the inside function. My derivative is 12x squared. Well, this doesn't say 12x squared, it says 7x squared. But again, it's just a constant mistake, so we can make do with that. Let's substitute for the function that's inside another function here. And then du would equal 12x squared dx. Okay, so this one's a little bit more complicated. We want to say 7x squared. So the first thing I'm going to do is I'm going to divide both sides by 12. So it's 1/12 du equals x squared dx. And I'm going to multiply both sides by 7. So it's 7/12 du equals 7x squared dx. So now 7x squared dx I can replace with 7/12 du. And then I can replace what's under the radical with my u. So now this becomes, I'm going to bring my 7/12 out in front here, 1 over root u du. Rewriting this so that it's easier to take the antiderivative, I get u to the negative 1/2. Taking my antiderivative, I get u to the 1/2 over 1/2 plus c. Simplifying and back substituting, I get 7/6 root 4x cubed minus 5 plus c. Or if you want to leave it as 4x cubed minus 5 to the 1/2, that's fine too. We can perform integration by substitution for more complex trig functions as well. Let's take a look at question A. So again, we want to substitute for an inside function. The inside function here is 2x. So let's go u equals 2x. Du equals 2 dx. So 1/2 du equals dx, because we're just looking to get rid of dx here. So this is going to be 1/2 sine. I replace 2x with u, and I replace the dx with 1/2 du, so it's du, the 1/2 on the outside. Taking the antiderivative of sine is negative cosine plus c. Resubstituting, I get negative 1/2 cosine 2x plus c. Now you can always do that for a problem like this, but we'll do so many of these. So a problem as simple as this, you might start just to recognize the pattern, and you might not even need to go through the substitution process. This one, so we're going to substitute u is theta over 4. So du equals 1/4 d theta. But we're not looking for 1/4 d theta, we're just looking for a d theta, that's it. So that would be 4 du equals d theta. So over here, I'm going to write 4 antiderivative of cosecant squared u du. So for the antiderivative of cosecant squared is negative cotangent. And back substitution would give us this is our final answer. This one looks a little bit tougher, but what we want to do here is we want to substitute for sine 3x, okay, because that is the function that's inside the squared function. And our derivative of that is going to be 3 cosine 3x. But if you look at our original problem, we're not looking for a 3 cosine 3x. We're looking for a cosine 3x dx. So I'm going to just divide by 3 here. All right, and I get cosine 3x dx is equal to 1/3 du. So I can replace 1/3 du, and then sine 3x just becomes u, so u squared. So I get 1/3 u cubed over 3 plus c, which is sine cubed 3x over 9 plus c. All right, this will also work for exponential forms. So here's our exponential forms. We have e to the u if u is something besides just an x, or a to the u, again, if u is something just besides an x. So for this one here, let's substitute for 3x plus 1. So then du would be 3 dx. So I can rewrite this as 1/3 du equals dx. And I can substitute in 1/3 e to the u du, which is 1/3 e to the u plus c. And our final answer would be 1/3 e to the 3x plus 1 plus c. Letter B, so we see the derivative of this would be 2x, well, negative 2x actually, and this would be 5x out here. So again, it's just a constant that is screwing us up. We can deal with that. Let's let u equal negative x squared. So then du equals negative 2x dx. But we want a positive 5x All right, so if I divide both sides by 2, negative 2 actually, and then if we multiply both sides by 5, I can substitute in negative 5 halves du, all for 5x dx. So that all goes in for 5x dx. And then e to the u. Negative x squared becomes u. So then our antiderivative would be negative 5 halves e to the u plus c, or negative 5 halves e to the negative x squared plus c. Question C. We have 1 over x, which is our inside function here. So let's substitute u equals 1 over x, or x to the negative first. Du would be negative x to the negative second dx. All right, if I divide both sides by negative 1, I get negative du equals, I'm going to rewrite this as 1 over x squared dx. Hey, look at that. We have 1 over x squared dx right here. So that's all going to be replaced with negative du. So negative du, and then the 1 over x just becomes u. My antiderivative is negative e to the u plus c, or negative e to the 1 over x plus c. This one, we have our inside function is cosine. Cosine is inside e to the u. So my derivative would be negative sine x dx. Divide by negative 1 on both sides. We get sine x dx, which is exactly what we're looking for right there. So now I can replace that with negative du and replace cosine with u. And now I can take my antiderivative. Resubstituting back in, I get negative e to the cosine x plus c. This also works for logarithmic forms. All right, the 1 over u that we've always been doing with this, 1 over x before, but now it's 1 over u. All right, so if we see something that has a rational function, where there's functions of x on the top and bottom of our function, we probably want to use substitution, and we probably are going to want to substitute for the denominator. If we take our derivative, we would get 6x minus 2 dx. Oh man, that's great. Look at that. 6x minus 2 dx is exactly what we want it to be. So I can replace the entire numerator and dx with just 1 and a du, or just a du really, and the whole denominator becomes u, which are absolute value of u, so natural log of absolute value of u plus c. And back substituting, we get natural log of the absolute value of 3x squared minus 2x plus c. Same thing here. We see that the tangent's in the bottom, and we see its derivative is in the numerator here. So I'm going to substitute for the tangent. And I got du equals secant squared x dx, which works out well because that's exactly what we're looking for. So this is going to be 1 over u du again. Natural log absolute value of u. Natural log absolute value of tangent x plus c. Okay, we're going to stop this video right here for now. We will pick up more substitution in our next video. We'll call this our substitution video part 1. Come on back next time for substitution video part 2.